Welcome to Robotics and Automation News webinars, where you can be part of a global event without leaving your home or office. Attend our live webinars and communicate directly with influential professionals in your industry.
Hello, my name is Abdul Montakim. I'm editor of Robotics on AutomationNews.com. I'm here to take part in a webinar given by Nvidia, in which a presentation will be made by Professor Dieter Fox, a roboticist at the University of Washington.
Yeah, I'm going to give you an overview of kind of the kind of things we want to do here in the lab, and also a little bit more specific information of some of the things we're doing specifically at the open house tomorrow. Can you all see the slides?
Yeah.
Yeah.
Yep.
All right, great. Let me see if somehow my page down doesn't work here. Okay, now it does. Embargo slide. We went through that. Let me first maybe briefly tell the story, like how all of this came about. And so I'm a faculty in the School of Computer Science and Engineering at the University of Washington, and I met with Jensen Huang, the CEO of Nvidia. We met at a research conference in summer of 2017, and we talked about robotics and the future of robotics. And again, my research area is in artificial intelligence and in robotics. And at the time, I think the way I look at this is kind of, if you think about what we see right now going on in the robotics domain, and at the kind of, let's say, robots that are actually being deployed, that are very close to being deployed, then I mostly think about the systems that you can see on this slide here, where it's about robots that are mostly, let's say, navigating around, like, for example, let's say the Kiva system in a fulfillment center, or robots now that are coming up more and more that can move things throughout a warehouse and follow people. We have many of these robot systems that can be deployed for delivery purposes. We can see them coming up in hospitals and in hotels. There are certain systems out there. And the newer systems, as you see on the slide, kind of the one in the centerpiece on the lower one, is robots that might start doing delivery systems, more also from house to house to your door. And if you think about it, then the real goal of these robots is more or less getting from A to B without crashing into something. Okay, so which means they use their onboard sensor data to do navigation tasks, but it's all about avoiding contact with things around them, right? They want to move around obstacles. They certainly want to move around people and things like that. If we look at other kinds of robots, for example, in industrial manufacturing, like you can see on the lower right, so these are robots that clearly generate, let's say, physical contact with the environment, because if you want to build a car, they have to pick up the doors and move them to certain locations so that they snap into place and things like that. But what's really lacking here is, as you can see, there's virtually no people around these robots. If you look carefully enough, you can see one person in this factory there on the left side somewhere. But these kind of manufacturing manipulators, they are really geared towards highly repetitive, highly precise tasks that they can follow over and over again, thousands and thousands of times. And there is no flexibility in how they perform that task. So it's all about doing the same motion over and over again. And you want to make sure that, for example, there's no person anywhere close to that robot. So this is kind of how we see what's going on in robotics right now and these kind of application domains. But I think what's going to happen kind of with this next generation of robots is what you can see of these slides that looks, I think, very, very different, where we have robots that are interacting with people, and that are robots that physically interact with the environment, which means, for example, in these contexts here, these robots, they need to pick up objects, they move them around, they get even in physical contact potentially with people. There are many application domains for these kind of systems. So you could imagine what we call smart manufacturing, where you have robots that can be programmed by a person very easily. These are robots that can actually operate next to a person, and they don't have to be caged away. Robots that help people with physical disabilities, like you can see that system here that a colleague of mine at Georgia Tech investigated is, for example, help shaving a person that is quadriplegic in this case. So they did some studies what kind of tasks such a robot could do. Or in general in the healthcare sector, helping elderly people. And again, it's a very, very different view from these kind of robots that you saw on the previous slide, because here it's about we need to do physical contact with the environment, and we need to react to people, and we need to do so very closely to them. Okay, so of course what you also realize is that there's still a lot of research in order to really enable these kind of systems. So this is just at the beginning, and that is why Jens and I agreed that there's enough research to be done that we should actually start a research lab here in Seattle on that topic. And the key goal is really that we want to do open-ended basic research that will enable this next generation of robot manipulation systems that are interactive, that can solve tasks safely and interactively with people. And again, I think this area has broad applicability, for example, robots in the healthcare sector, in the home, and in this industrial manufacturing settings. On the next slide, I want to just briefly show you, like, this is the lab that we just moved in November. So we've been looking for a location that was close enough to the University of Washington. So we are here 20 minutes walk from the computer science department or the building of the computer science school, so that we can closely interact with the university. One of the key features is that the research we are doing is open and publishable, which means we publish our work and the progress in the main conference and journals. And that also makes it much easier to collaborate with universities, where, of course, this kind of dissemination of ideas is a crucial component. Okay, so again, the idea of being close to the university enables us this really close connection. For example, we have students from robotics who do robotics at the university. They spend time with us here. Some of them are doing internships with us. Some of them just come in for a weekly meeting. We are co-advising them on their PhD projects, and also coming, for example, to seminars and things like that. The space is, I think, comfortably large, which is really nice. So we're aiming also to have like 50 robotics researchers here, which is partially Nvidia full-time research scientists, but also currently, for example, we have 2 faculty that are visiting us. So one of them is on sabbatical, and he decided that our environment is exciting enough that he wants to spend the sabbatical with us doing research. And also, of course, good sets of student interns doing their summer projects or even throughout the year with us. So the kind of team that we assembled is attractive enough that we're getting actually students in the summer that come from all the top universities. So be it, we have several from the University of Washington. If you look at Stanford, MIT, CMU, Berkeley, all the main schools that do robotics, Georgia Tech, they all send their students to us to do interns so that they can learn from the expertise that we have here. The main kind of philosophy behind the research that we want to do here is, first let me tell you where me coming as an academic, what I sometimes found somewhat frustrating is that the kind of research that we are doing often in these university labs are kind of small projects. Because if you imagine a PhD student, they want to write their PhD thesis, so typically they focus on doing a project so that they can publish a conference paper on it or a journal paper. And then when you want them to kind of integrate that into a larger scale system, then typically they are hesitant because nobody rewards them for that. What they rather would want to do is say, oh no, now I got to do something different because otherwise I can't write my next paper. So we've all seen that in academia. And another problem in a lot of the research that we see in robotics is that it's driven by these subdisciplines that don't really collaborate very closely. And by subdisciplines, I mean that there are many different areas that have to really work together if we want to build this next generation of robots. So we have people coming from robot control. We have people coming from computer vision is a crucial area. Deep machine learning. natural language understanding, human-robot interaction. All these areas I believe, have to really come together and collaborate in order to really build these next generation of robot systems. So in this lab specifically, then what we're looking at is, on the one hand side, we want to do research projects that are focusing on these integrated systems, and I'll tell you a bit more about that on the next slides. And the team that we have assembled really want to bring experts from these different areas together, but they're all willing to work towards these robotics domains. Okay? Oh, by the way, if you have questions, don't hesitate. Are we good to move forward for now?
Yeah.
Okay.
Yeah.
Okay. No, I just wanted to make sure. So now, one of the main things was then we wanted to decide, okay, what would be a good test case or challenge scenario or environment in which we could build out our research, right, and test our robots in. And that brought up this notion that we believe that the kitchen environment is actually really well suited for this. So what we do here in the lab is, what you see in the upper left on that picture is actually, we just went to the local IKEA store and bought a kitchen and put that in the lab here. So this is a fully functioning IKEA kitchen. And the idea is that we want to design and build our robot research around challenges that come up if you want to have a robot do things in this kitchen. Ultimately, what you can see on the lower left is just a mock-up scenario, but ultimately you can imagine, well, why shouldn't the robot be able to cook a meal? Okay, but toward that really long-term goal, there are many sub-challenges that of course we have to work towards, right? But let me briefly say why I think the kitchen is an exciting test case for this kind of research. First of all, you can make it as challenging as you want, right? Which means if we can solve the general kitchen cooking problem, then I think we can do virtually anything with these manipulators. Right? And it's not only about robots, but it's also about robots alongside people in this kitchen environment. So we think this is a really nice environment that can be phrased as a challenge scenario for the whole robotics community. Not just for this local lab here, but other research labs that work on manipulation. This can become a really nice test scenario on which different ideas and algorithms can be evaluated and compared against each other. The kitchen, there are many different research challenges you can investigate in that area. Obvious ones are grasping objects, picking up objects, moving them around. But if you imagine, this can become much harder when you think about food preparation. How do you peel and slice an onion is certainly not a trivial task for a robot. Or imagine you want to have a robot bake a cake, then suddenly you bring in milk, eggs, flour. How do you reason about this? How do you robustly manipulate those kind of things? But also other areas are human-robot interaction. How can the robot help a human cook a meal? So kind of the sous chef. How can the robot just bring the ingredients that are necessary for a recipe? And that also asks questions like what we call activity recognition. So for example, if a robot wants to help you cook a meal, it first needs to know, for example, what the recipe is, and then it should recognize what you are doing right now so that it knows which ingredient, for example, to bring you next. Other really interesting challenges in this domain will be what we call natural language understanding. So for example, if you have a robot operating next to you, you don't want to type into like your computer, for example, what the robot should do. You just want to tell it what to do, right? So imagine things like the smart speakers. Is it called smart speakers that we have in the home? Like the Alexa or the Google Home and the Apple device. You want to interact with a robot, I think, in a way you would do with one of these devices, which means you just want to tell the robot, okay, now bring me the eggs. Or if the robot doesn't know where they are, you just want to be able to say, oh, it's the second drawer from the top. Now, there's a lot of research that still has to be done on getting a robot to actually understand these language commands and execute them in the real world. And again, as I mentioned early on, I think one important aspect of why we chose the kitchen, it's not necessarily, for example, that I believe the kitchen is the first killer app for the robot in the home or the next generation of robots, but I think it's just really well suited to represent all these other challenging domains that we face in next generation manufacturing. Also, for example, in hospitals, right? Like even in hospitals, robots might have to move around and might have to open doors and drawers and get medication and things like that. And also in other settings like nursing homes or fulfillment centers. So this is kind of, yeah, of course.
Is this a standard sort of human scale kitchen? Because even with multiple humans in a kitchen, it's very easy for them to get in each other's way. So
yes.
Simply being helpful without being in the way is a significant challenge for a robot.
Absolutely, that's an awesome question. So first of all, yes, this is literally an IKEA kitchen. So we literally went to the IKEA store and said, okay, this is what we want to buy. So we didn't make any modification to that. And this is one of the research projects we really want to look at. So for example, two of the research scientists that just joined us in the last month are computer vision experts that also look at, for example, human body tracking. So for example, for a robot, right, to navigate around a person and not bump into the person, you need to detect where the person is. Then of course research challenges are you want to anticipate how the person is moving and react to that. So this is exactly one of the research projects that we want to look at. Great question. Any other question? And again, the main point here is that we want to do the research really in this environment, right? We don't want to do it, for example, purely in a simulated or mock-up scenario. We really want to challenge ourselves to do it in the real world, in a setting that you would face there as well. Okay? So now this is of course what you see here on the lower left here. This is future, right? This is kind of where we want to go with it in these challenging settings. What we want to show here in the open house tomorrow is a first baseline system for a robot that can at least do some kind of manipulation tasks in that kitchen. What you see on that slide here is the robot that we have here in the lab right now. This is not the ultimate kitchen robot system. It's just something that we were able to put together based on the different hardware we had as our first demonstrator, because we wanted to set up a demonstrator rather quickly. So the idea is what you see in black down there. This is the navigation base, which is Nvidia also has a system called Isaac SDK, which is a software system for in general for robotics that they've been building out for a navigation platform. So what you see down there is the Isaac SDK main navigation platform. It's called Carder. And what we did is we just put one of the manipulators that we purchased and put it on the Carder, and now we have a mobile manipulator. Okay, so at least what we can look at now is how can we move through the kitchen and, for example, open the drawers and doors, and how can we then, for example, pick up objects and move them around. Okay, so the idea behind this is that this first system is that it represents the real key baseline that you really need to solve, right? And the subcomponents that really belong there is the robot must be able to recognize objects. So if you want to pick up, for example, in this picture, the yellow mustard bottle, the robot needs to use camera data to recognize where that mustard bottle is, because we don't want to tell it that. It has to see that by itself. It has to be able then also to track it, or when it's opening a door or drawer, it has to kind of be able to track where the door and drawer is right now. And finally, of course, it has to be able to pick these things up and move them around. Okay, so these are the key components that we put together on these robot systems and integrate them into that so that the robot can actually perform these tasks. So specifically, the robot can move around, it can see, for example, here these objects, it can detect them, it can estimate exactly where they are. It can also open the doors and drawers and, for example, grab an object and move it to a desired location. Okay, and the motivation behind that is twofold, I think. On the one hand side, again, we want to use this for our own research so that we can build on top of that and approach all these other challenging tasks. As you asked, for example, about now, if we want to do that next to a person, right? How can we do that safely? But before you can do that next to a person, the robot first should be able to do it robustly by itself. Okay, and the other piece is that the software components that we have, so this is all state-of-the-art research components that address these individual problems that we developed over the last here in the lab, but also already at my University of Washington research lab, part of them. The idea is that we want to share that with the research community, so that, for example, if there's a lab at some other university and they say, well, I want to do research with robot manipulation, but I don't want to worry about these low-level details like figuring out where the objects are or how to open a door or drawer, then they can use our system and deploy it in their lab without having to reinvent all these tools. Okay, so the design was also so that it makes it very easy. So all we require for this robot to do this is actually we just need a 3D, what we call a 3D model of the kitchen. And we need 3D models of these objects. And once we have these, the robot can then do everything by itself, which means if you want to run that system in your kitchen at home, let's say, what you have to do is, let's say you measure out your kitchen, build a 3D model, and then the robot can do these kind of things that it can do in our kitchen. And one portion there is, on the one hand side, you might say, well, that's crazy, I don't want to measure out my kitchen. But you can imagine in the near future, if you buy a kitchen at your favorite kitchen store, it should come delivered with its own 3D model, right? Because these kitchen designers, they obviously have 3D models of their kitchen. So why not buying that alongside with your kitchen, so that when you want to have a robot operating in it, it has already the 3D model rightly available from the beginning. And another motivation is also that in future research, we want to then perform the research such that we can do the same tasks without requiring models. So that I think more human style, where if you go in such a kitchen, you don't need a 3D model, right? You just say, when I open that drawer, which means I'm walking up to the handle and I'm going to pull on the handle and then I'm going to open the drawer. So that is also exactly the kind of research that we are addressing right now. Okay, so future work then goes really into these notions of what we call lifelong learning, that these robots can continuously learn and improve from their own experience. They can learn about new objects. They can get better and better at what they are doing. So for example, you could imagine if you put such a robot in your kitchen or your hospital or so, that robot on the first day might not be able to do everything perfectly well. But I think after some training, that robot should just be able to do it really well in your environment. Okay, and then of course, the human-robot collaboration is going to be a really crucial part of the work we want to push forward. Here you see one other aspect that I think is going to be very important for the research we are doing, but also I think for the research community in general moving forward, which is simulation. And Nvidia, of course, which I find exciting, is of course immensely experienced when it comes to physics-based simulation, photorealistic rendering, and that comes of course a lot from the game engine background. Right, so Nvidia already has simulation engines, which is one of them is called Isaac Sim, that perform physically accurate simulation of environments and photorealistic rendering. So what you see here on this picture, for example, let's look at the lower left one. This is actually our robot simulated performing tasks in a simulated version of our kitchen. Okay, so we worked with the Nvidia simulation team to get a one-to-one model of that real-world kitchen in simulation as well, so that we can investigate how, for example, how realistic is the simulation, how can we use that simulation to train our robot so that we don't have to do all the training in the real world, how can we use that simulation to train the robot to recognize objects and things like that. So I think overall, for robotics community and research moving forward, using more and more of this simulation tools that are coming up now is going to be a huge magnifier in how fast we can make progress. Okay, so with that, I'm coming to the last summary slide, let's say, where really the goal is we want to enable this kind of next generation of robots that can interact with people, that can do manipulation tasks in open-ended settings, and do that very robustly. So to do this on the research approach is really that we want to combine recent advances that people have come up with. On the one hand side, what we call modeling, which means, for example, we know a lot about the physics of an environment. For example, we do know what gravity is. We do know what the mass of an object means or what the friction of a surface means. We can model these things using real physics models of the world, but we want to combine these model-based approaches with these recent advances in deep learning, which is this revolution of like using data to learn, for example, visual perception tasks and also robot control tasks. The team that we're putting together is really, we're focusing on an interdisciplinary team so that we not, for example, have people that know about robot control, but we also know about computer vision, language processing, and deep learning, for example. We are going to use the kitchen as one of the real benchmarking and development environments that we're also going to share a lot of our insights with the research community so that they can build on top of these kind of things and hopefully use this also as a way to benchmark and develop their own research progress. And I think overall Nvidia is just extremely well positioned to move this forward, because if you think about what we need for this next generation of robots, is we need robots that have very strong perception capabilities, which means they need to analyze camera data. They will have touch sensors that they need to analyze. All of this has to happen in real time. And of course, as you can imagine, GPUs are kind of the prime compute base already that do this kind of work. And also for learning, machine learning, deep learning, all of this, of course, leverages already a lot of the GPU-based computing that Nvidia is doing. And finally, just to bring this notion up again also, I think the location here next to the University of Washington, which is one of the prime research centers, of course, especially also in computer science and in robotics, is going to be beneficial both for the lab moving forward and also for the university to have an increased team of robotics researchers around. And I think this is it. Open for questions.
Yes, Dieter, Professor, it's Abdul. I've got a few questions actually,
Yeah.
if you don't mind. I'll try and limit them to maybe one or two, but I thought of quite a few. I thought, if you don't mind me sort of interpreting in a sort of very broad brush way, the kind of robotic system that you're trying to develop seems to be humanoid in the nature of its activities. I know it looks like a robotic arm and all that, but as you said yourself, the idea of the way a human comes into a kitchen and assesses the situation, the dimensions, the individual objects that they need to manipulate, that's what you eventually want to integrate or emulate in your robotic systems. If that's a correct sort of analogy or metaphor, I was wondering if you could answer the question about why this area of robotics is so difficult, humanoid sort of human-type activity, human-type movement and manipulation is difficult, and also is the human way of doing something necessarily the best way of doing something? The reason I ask that is because in the area of, I don't know, things like software like AutoCAD and Dassault Systems, various software, they have something called generative design, where they allow the computer, the software, to come up with a design for a particular object, and the software, what it returns as a result, as a design suggestion, is completely different to what a human would suggest as a solution for that. So I was wondering if you could comment on those things. I'm sorry to throw several questions.
Yeah. No, that's super exciting. That's a really nicely mesh also to kind of really these broader research visions here, right? And I think great that you're asking that. So first I want to clarify, when we say humanoid, systems, you do not, I think, necessarily mean, let's say, humanoid robots that walk on two legs or things like that, but you're referring a bit more to, let's say, the human way of doing things, right? I would say actually that our goal is not to do things the way humans would do them, but we're taking inspiration from human capabilities in what they can do. So, for example, if you know, for example, human hands, how humans interact, how we can interact with objects, pick them up, move them in our hands, is just absolutely amazing. And in robotics, we are not anywhere near to these kind of capabilities right now, right? And I think the techniques that we deploy here are, again, we're not trying to do things on the technological side the way humans would do it, but we are motivated by this notion of, for example, even a robot, even if you ignore the fact that we want them to do it, let's say, the humanoid way, they need to have certain capabilities in order to operate in these kind of environments, right? So, for example, any of these robots, they must be able to pick up objects, right? If you want, for example, a robot to help an elderly person or a person in a wheelchair pick up an object, pick up a glass of water or something like that, that robot must be able to do these kind of tasks. And one could now say, well, we could do it in a, let's say, purely robotic fashion, which I'm not even sure how that would work, but we could say, oh, we design everything so that it's easier for the robot. But I think ultimately these robots have to be able to operate in human-built environments, and therefore they have to be able to operate on objects that they might not have seen before, right? So these kind of abilities of constantly learning and constantly improving, I think, are actually really crucial if we want to get these robots to be robust in these, what I call, open-ended environments, right? Because it's not about, so if you compare it, for example, to the current industrial setting, right? In these environments, everything is designed for the robot, which means everything is constrained such that the robot can execute it. If we want to get robots out into the real world, then they must be flexible enough to react to the environment, because the real world is not designed for these robots. So again, I think it's not that we say we want to build robots and replicate the kind of way humans reason about it or do it, because these are really hard and open AI challenges, right? There are different approaches also to the grand AI problems in general. But I think we are more inspired by the human ability and flexibility in solving these kind of open-ended tasks. Does that make sense?
Yes, it does. Appreciate you answering, as I say, a complex, compound question. If I could follow up with that, you touched on it a little bit towards the end of your answer. I was wondering, I have asked this before of other people, are the challenges more of a software challenge or more of a hardware challenge, in the sense that obviously with software, with virtual, anything virtual, you can get it to do anything, all sorts of things.
I think.
Yeah, go on.
Good. I think on both ends there are still big challenges, right? So, for example, people show. So, on the one hand side, one could say, "Oh, our robots are not good at manipulation because their hardware isn't good enough," right? But I think that's not correct, because there have been examples where people remotely with a joystick controlled a robot manipulator, and they showed that you can actually do a lot of stuff with a robot manipulator if you know how to control it well with human, let's say, remote control, right? So I think one of the key challenges is really on the software side, developing algorithms that have these learning abilities, right, and these perceptual capabilities of recognizing objects and thinking about how should I pick up this object, right? These are all kind of software questions. I think the super hard hardware question is the design. That's also, I think many people in the robotics community agree with that, is the design of hands and touch sensors. We also here, we have one of our manipulators has actually a 4-fingered hand. It's called an Allegro hand that has touch sensors in the fingertips, but I think the hardware is still not anywhere near to the kind of touch capabilities that the human hand has. So I think that is clearly one of the big areas, open areas. And what's interesting is, for example, in this kitchen setting, designing a robot that is really well suited for this manipulation in such a kitchen. For example, if I go back this slide and show you the robot that we have, this one, that's clearly not going to be the solution, right? So we want to have robots with 2 arms. One big problem is, where do you put the cameras, right? Do you put them into the grippers? Do you put them somewhere on the robot, but the camera needs to move? And these are the kind of things you learn best by actually doing the research in the real world. Because initially I would have thought actually, oh, that's going to be easy. We'll just put a camera on the robot and it's solved. But now if you want that robot to be able to, for example, look inside a drawer, then you might actually need to be able to move, let's say, the camera around in order to look there, right? So right now, again, because we wanted to put together this demonstration system, if you look carefully, you see that there's no camera on that robot. And that is because we didn't have time to put this system together yet. Our algorithms can all handle a camera on the robot, but we actually, I don't know whether I have a picture there, you can't see it, but in this kitchen we actually put 2 depth cameras from the ceiling that observe the cabinets, right? But the next step will be to put these cameras on the robot itself. So there are many, I think, hardware design questions that we will still have to address. But again, the big challenges also come from the software side and the machine learning, deep learning, all these kind of questions.
It's interesting that you're talking about touch sensors. I was thinking about how a task that's very easy for humans has a whole lot of real challenges for a robot. Mm-hmm. I made an omelet yesterday.
Oh, yeah.
How do you make an omelet without getting eggshell all over the place or smashing your eggs all over the counter?
Yep.
Oh,
totally. Or how do you swirl, let's say, the egg a little bit and those kind of things, right? And why we humans, and that's a point, I'm not sure whether I made that before. One of the real key approaches that we are following is this what we call real-time closed-loop control, which means whatever the robot is doing, it's in real time constantly looking at its sensor data and tries to adapt at what it's doing. So for example, if you want to swirl an egg with a fork, let's say, right? You look into the bowl, you swirl the egg, at the same time you actually maybe use your ears to listen what it sounds like, you use your eyes to look at what the swirled egg looks like, and you use kind of your force sensors, your touch sensors, in order to figure out how to move the fork in all of this, right? So we humans use all these different sensor streams to solve these problems, and I hope that by forcing ourselves to do our tasks in these integrated systems and in these real world tasks, we're going to really learn about them and hopefully then make the big progress too.
I would just ask one more thing. I came across the word mechatronics a couple of years ago when I started covering robotics. It's a very interesting word, obviously, combining mechanics and electronics. Is it time to update that or add something to it now? Because things have become so complicated, as you were saying about sensors, the cameras, and all sorts of things. I think broadly they can probably be fitted into mechanical and electronic things. But what are the most important things, I suppose, now? You said you listed a few of them: vision sensors, touch. Those are the things I remember you saying.
Yeah.
What can you say? What can you say is the new sort of thing?
Yeah.
In terms of
yeah, that's
a combined together.
Good point. I think it's this co-evolution of the software and the hardware, right? And that we need these software systems that, as you say, take advantage of all this multimodal data and combine it. But crucial is that we are combining, for example, in robotics, what is really often separated is what we call perception or estimation from control. So we have people that focus on analyzing, let's say, camera data to detect objects, and then we have other people that focus on planning how to move a manipulator to pick up an object. But I think we need to view all these kind of problems, these sub-problems, in a joint and unified way, where we design both the control and the perception side along with the hardware in order to come up with these kind of really robust techniques that take everything into account.
I find it quite interesting, just final point or question, I don't know what it's going to be, but I find it quite interesting that you mentioned the four-finger sort of end effector, but I find it quite interesting that roboticists don't dwell on or preoccupy themselves with essentially copying the human hands and programming for that, and because it is a very complex part of our bodies, and our brains develop a lot of processing power to manipulating our fingers and hands, and I would have thought that kind of situation would be replicated in robotics as well. And I would also wonder, edge computing is something that I've heard of, but the embedded stuff, I mean, where computers embedded, you could see a situation where there might be embedded computers in the wrists and the fingers of these robots, processing a lot of the very near stuff that they're doing, whether it's touch or sensor. But I don't know, your comments on that?
Exactly. So 2 points you said about hands. So there are people in the robotics community that focus on design of hands. Actually, an ex-colleague of mine at the University of Washington, Yoki Matsuoka, she was extremely well known. She built a hand called ACT hand, an atomically correct testbed hand, where she actually measured the 3D structure of the human bones and tendons and tried to replicate that in a robotic hand. The problem is it was so complicated that it actually never really worked. So I must say, I personally don't submit to the notion of that a robot hand has to look like a human hand. So at this point, I think even 2 fingers or so are already pretty useful in many settings, right? Humans are able to do extremely good, many things with just 2 fingers. I think, again, there are people in the community looking at these aspects. It just seems extremely hard also to incorporate these touch sensors into them, because the hands are moving, and then how do you integrate the touch sensing and all the cabling and these kind of things. And then the other point you made was, remind me?
I was just wondering about how, for example, Nvidia chips or sensors.
Oh, yeah.
Where they're embedded in the arm of the hand or...
Yeah, exactly. So actually we are looking at, so one thing I strongly believe is, for example, for this robot that let's say our next version of a robot that will navigate through the kitchen and have 2 arms and things like that, will certainly have cameras in the hands as well. I agree that I think it's not going to be one monolithic camera or so, but it will be multiple of these somehow placed throughout the body of that robot. So for the closed up perception and things like that, as you said. Computation wise, I am not, to be honest, I'm not sure if we need specialized processing, let's say, inside that hand, right? But you're right, that could be an interesting aspect, right? Like to avoid all the cabling or things like that. But I must admit, I haven't really thought deeply about that yet.
Yeah, it's an interesting one. I don't know. Obviously, humans have one brain and it's in our heads, well away from our hands. So I suppose that's the model. But I haven't heard of anything where the embedded chip is further towards the end effector.
Yeah.
In the end effector. But a very interesting thing. I suppose one more bonus question. What do you see as a commercial outlook for yourself in terms of, do you think there'll be any prototypes and commercial products in the near future, or what are you hoping to be able to take to the market, as it were?
Yeah, good point. I think so. On the commercial side, I think the first successes will be more on the navigation, robots that navigate. I think for the manipulation, the lab here, we are focusing at this point really. So Jensen Huang, the CEO, takes actually a longer term view on that, where he says we first have to build and develop the basic capabilities that these different application domains need. And I think one of the more immediate ones would be, of course, I guess, a smart manufacturing, right? Where we are going to build robots with the capabilities to robustly pick up unknown objects and interact with people, and can be trained to do new tasks much faster than they do right now. So it turns out, as far as I know, actually, in many of these industrial settings, the most expensive acquirement is not the hardware cost of a manipulator, but it's the cost you pay to the company that reprograms your manipulator if you want to change the task. And I think in the near future, we will be able to have robots that are flexible enough so that it will be pretty easy to reprogram them to new tasks. And that is also something, of course, that many of these companies are pushing towards, right? Manipulators that can interact with people and are safe around people. I think this will be the closest in commercially viable system there.
Okay, everybody, I know we went a little bit over. Just wanted to kind of reiterate that we're going to go ahead and send you a package of materials right after this call. Photos and videos will be sent over tomorrow morning. And if you have any additional questions, feel free to reach out to me. We're happy to answer them.
Thank you very much.
That's great.
Thanks, everybody, for your time.
Awesome. Thank you.
Thank you.
Bye.
Bye.
Send us an email at sales@roboticsandautomationnews.com to register for one of our many upcoming webinars. And if you'd like us to host your webinar, we have a range of options, including long-term lead generation packages and marketing campaigns. We look forward to hearing from you soon.